At 30 degrees Celsius, pure water and a solution of ethylene glycol have nearly the same vapor pressure. As temperature increases, so do both vapor pressures. But when the vapor pressure of water reaches 1 atmosphere, ethylene glycol is at almost half that. Pure water boils at a significantly lower temperature than does the ethylene glycol solution.
Because the solute is blocking the solvent from going into the gas phase, the vapor pressure at a given temperature is usually lower than the solvent, okay? So an example there in that video, at 100 degrees Celsius, where water by itself boils, the ethylene glycol was only about 400 millimeters of mercury, quite a bit less vapor pressure. So it takes an extra amount of energy, i.e. an increase in temperature, in order to get the ethylene glycol solution to boil. And this delta T, all right, which you can see in the lower right kind of picture right there, this delta T is nothing more than a little bit of extra temperature to get the solution to boil. So while water boils at 100 degrees Celsius, maybe the ethylene glycol solution boils at like 110 Celsius. So the delta T would be 10 degrees higher. And we'll see how you can actually calculate, by the way, those delta T values. But the important part here is that all solutions will boil at a higher temperature than the pure solvents they came from. So if you have water, it boils at 100 degrees Celsius. If you start putting sodium chloride, a solute, in the water to make a sodium chloride solution, the solution will boil at a temperature higher than 100 degrees. This is called boiling point elevation, and there's some really cool things that you can do with this. The equation that's used for boiling point elevation is delta T equals K times M. M is molality, so moles of solute per kilogram of solvent. K is a constant that depends on the solvent you're looking at. And if you look in the lower bottom part right there, these values on the left of my red line, those are all boiling point K constants. And it depends on the solvent you're using. So water is 0.51, benzene 2.53, etc., etc. We'll talk about the freezing ones to the right of my red line in a little bit. If you multiply the molality times the K, that's going to calculate the change in temperature, how much higher the solution boils relative to the solvent. So you can see that the amount, the delta T amount, will depend on the molality, which is how much solute you have in the solvent, but it does depend on the type of liquid as well. Here's an example of how this works out. So let's say we have, again, 62.1 grams of the ethylene glycol, which is 1.00 moles, in 250 grams of water. And it says, what's the boiling point of the new solution? Now, water normally boils at 100. Our answer here had better be a number that's larger than 100 degrees. Now, to answer this, we're going to need the K value for water, and it's 0.512. If you look in the textbook, that's what pops up. And delta T, the amount of temperature it's going to be higher, equals that K value times M. So the molality, as we saw in a previous example, was 4.00 molal. That's the little m. And we'll multiply that number by the K, by 0.512, to calculate delta T. If you do that, delta T comes out to be 2.05 degrees Celsius. That's the amount that the boiling point has increased. So water normally boils at 100. We're going to add 2.05 to it. The boiling point of the ethylene glycol solution, 102.05 degrees Celsius. So this is the effect of having a solution. Boiling points are higher. But there's another effect that happens with solutions. So far we've seen and talked about how the vapor pressures are decreased and boiling points are increased. But another thing happens when it comes to freezing points. Now, the freezing point of pure water is 0 degrees Celsius, all right? And that will happen when liquid molecules going to the solid phase are equal to the solid molecules going to the liquid phase. We're going to see that solutes act as blockers once again, but instead of blocking liquid going to gas, they block liquids going to solids. So it's going to take extra cold temperatures to allow the liquid molecules to form on the solid part. The punchline here is that if you have a solution, the solutions will freeze at a lower temperature than the pure solvents. And I'll show you some videos here in a second. But I do need to apologize for these videos. Both of these videos show the pure water with ice cubes at the bottom of the beaker. And like we talked about extensively with hydrogen bonds, the density of ice is less than the density of liquid water. So ice cubes are supposed to float, all right? And these videos show the ice sinking to the bottom. So I apologize for that. However, the ideas are still sound. Just ignore this animation typo.
When water freezes, its molecules leave the liquid phase and attach to other molecules in the solid phase. At the freezing point, an equal number of molecules move into and out of the solid phase. A solution of ethylene glycol, automobile antifreeze, has a freezing point lower than that of pure water. Molecules of the solute block the interface between the solid and liquid phases, thus decreasing the rate at which molecules leave the liquid phase and attach to the solid.
So in a pure solvent, all right, liquids going to solids have to start happening. There is always some solid going to liquid. It's an equilibrium like we've seen. In a solution, it's the solute that blocks the liquid particles from going to the solid phase. So you have to make the solution even colder than you would with a regular solvent. The coldness makes it harder for the solute molecules to block basically the liquids going to the solid phase, and that's why it takes a lower energy to make the freezing start happening. So in all that's said and done here, solutions are going to have lower freezing points than the pure solvents they came from. And that's another one of these colligative properties. This shows, this is actually basically the same things I saw earlier, but what's important here is that the equation for freezing point depression is almost identical to the equation for boiling point elevation. It's a delta T equals K times M. However, it's not quite the same. This is a delta T for freezing points, and the solution will be not as cold as, or the solution will be colder, than the solvent it came from. So it's a delta T freezing point, and that's equal to a different kind of a constant. It's a freezing point constant. So let me draw my little red line that I had on the previous slide. And while before we looked on the left for boiling points, now we're going to look on the right for the freezing point constants. And just like with the boiling points, every solvent has its own freezing point constant, K. So water is 1.86, benzene 5.12, etc., etc. And again, you have to think about the freezing points. So if we calculated, say, a delta T of 2 degrees and it was in water, then we would expect the water solution to freeze at -2 degrees. It would be lower than the freezing point it came from. So let's calculate the freezing point of that 4.00 molal ethylene glycol water solution that we talked about earlier. And again, the KFP, the freezing point constant here for water, 1.86. So just like before, we're going to calculate delta T first. Delta T equals K times M. So 1.86 times 4.00, the molality, comes out to be 7.44. Now, normally water freezes at 0, that means that the solution is going to freeze at 7.44 degrees less than that, or -7.44. So that's how you calculate the freezing points. Now, a little bit of a warning. Sometimes in certain textbooks, people will use a negative KFP value or negative KFPs. So instead of the 1.86, they might list it as -1.86. And honestly, that's fine. They're trying to correlate a negative K with a negative delta T. The only important thing you need to realize here is that molality, the M, it's like a mass, like molarity, and you can't in chemistry have negative mass ever, okay? So I don't care if your K is positive or negative. I don't care if your delta T is negative or positive. That doesn't bother me either. But the two things I do want you to know is that, first of all, molality is always going to be a positive number, no exceptions, all right? And whatever delta T you calculate, the delta T will be that much less than the regular freezing point. So in this problem, we had a positive 7.44. You need to be hip enough to know then that the freezing point of the solution will be 7.44 degrees less than the regular freezing point, so that's the negative 7.44. We haven't talked so far about the effect of ionic compounds when it comes to colligative properties. So far, we've been focusing on solutes like the ethylene glycol and iodine, stuff like that. Something strange happens with ionic compounds, so let's talk about that. So let's say this was a problem you had. You want to know how much sodium chloride was needed to dissolve in 4 kilograms of water, and we want to lower the freezing point by 10 degrees. So we want the freezing point to be negative 10 instead of the normal 0. Okay, no problem. So first we're going to calculate the molality. Remember that little m has to be positive regardless of what you do. If you need to absolute value the delta T and the K, that's not a problem at all. So solve for molality. Molality comes out to be 5.38 molal. So if we have a 5.38 molal solution, that's going to make the freezing point negative 10. All right, and that's not a problem. However, remember that all these colligative properties depend only on the number of particles and not the type of particles. And ionic compounds, especially if they're strong electrolytes, they don't stay as themselves. Like NaCl doesn't stay NaCl. NaCl breaks up into Na plus and Cl minus, i.e., you get more than one piece per mole. So for NaCl, you're going to get 2 moles of particle per 1 mole of ionic solute. The little m just represents total number of pieces, total number of particles, and you get 2 particles per NaCl. If you had something like magnesium chloride, MgCl2, that would break up into Mg2 plus 2Cl minus. You would have 3 moles of particle per mole of ionic solute. So ionic compounds, you must think about the number of ions, and that's going to reflect itself in these calculations. Back to sodium chloride. We need a total solution concentration of 5.38 molal, but that's 5.38 particles per kilogram, if you will, of solvent. There are 2 particles per mole of NaCl. So what you can do to get it into sodium chloride is you can essentially divide it by 2. It's 5.38 moles of particles. There are 2 particles per mole of NaCl. So if you divide 5.38 by 2, you get 2.69 moles of sodium chloride needed per kilogram of solvent. Now there are 4 kilograms of solvent. The sodium chloride molar mass is about 58 grams per mole, so you can turn 2.69 moles of NaCl into grams of NaCl and then multiply it by the 4 kilograms of water to get rid of that. You're going to need 629 grams of NaCl to place that in 4 kilograms of water, and that should make your freezing point 10 degrees lower than pure water. So the amount of dissolved particles becomes super important for ionic compounds. A person named Van Hoft, all right, Van Hoft is how I think people say it, came up with a small addition to the freezing point and boiling point equations. Instead of being just delta T equals K times M, you can add on delta T equals K times M times I. And I is called the Van Hoft factor. And the Van Hoft factor just represents the number of particles produced per mole, or officially number number of particles produced per formula unit. Ionic compounds are usually represented as formula units. So let's look at some examples. So ethylene glycol, like all organic covalent pieces, is just going to have an I value of 1. So we haven't talked about Van Hoft factor yet because all the examples I've shown you have been with covalent molecules. Things like ethanol and sugar and acetone, anything with nonmetals that dissolves well in water I've been using so far. If you have an ionic compound, then you just think about the number of pieces. So we saw earlier how NaCl breaks down into a positive and a negative. So if you have an NaCl, it breaks down to an Na plus and a Cl minus. That's 2 pieces. That's the theoretical value of this Van Hoft factor I. Calcium chloride breaks down into a calcium 2 plus and 2 Cl minuses. So you get 3 particles per mole of CaCl2. That's why the I factor is 3. Now we're only going to use what's called the theoretical values of I in Chem 222. Theoretical values are what they should break down, all is going well. A lot of times the actual values are less than the theoretical values, but that's something you can look at in future courses. We only really need to talk about Van Hoft factors with ionic compounds. Again, if you have something covalent, some kind of organic molecule that dissolves in water, it's not a problem. However, if you've got something organic, got to take care of it. Here's a question you might see. Which aqueous solution is expected to have the higher boiling point? And it's 0.10 molar sodium chloride and 0.15 molar sugar. And then it says pure water will have the higher boiling point. Well, first of all, C is flat out because all solutions will have higher boiling points than the solvent they came from. So C is just silly. And initially, you might think that answer B would be right because you can see delta T equals K times M. Molality, as it gets bigger, makes a bigger boiling point, so it'd be tempting to say B. However, answer A, sodium chloride, that's an ionic compound, and with ionic compounds, you no longer have I equal to 1. In sugar, I equals 1, but in sodium chloride, I equals 2. So an I factor of 2 times 0.10 is like 0.20, and that's bigger than 0.15 sugar times 1.15. K is the same in both of them. So the answer here is actually going to be answer A. Watch out for those ionic compounds. They will affect the boiling points and freezing points quite a bit, as you can see here. The real utility, though, of these properties comes from the ability to find the molar mass of a solute. Now, in the gas laws, we saw how PV equals nRT, and you can go about solving for the molar mass, which is really great if your liquid can be vaporized or it's for a gas. The colligative properties of boiling point and freezing point will allow you to find the molar mass of a solute under a lot more diverse kind of situations. And this kind of process is super handy. In the freezing point lab that we're going to do in Chem 222, we'll talk about a way that you can solve for the molar mass, stuff like that. This is an example of a boiling point problem, and we're trying to find the molar mass of azolene. And azolene is a compound that does dissolve in benzene, all right? And the normal boiling point of benzene is 80.100 degrees Celsius. With azolene in it, it's 80.230 degrees Celsius. And there's the boiling point constant, etc., etc. Now, because this is benzene, and benzene is very nonpolar, we don't have to worry about the Van Hoft factors here. These things are already going to be nonpolar. I factors equal 1. So we're already, we're out of the realm of ionic metals plus nonmetals. We're just going to use delta T equals K times M. If you're trying to find the molar mass of azolene, azolene is the solute. So we want grams of solute divided by moles of solute. And 0.640 grams, that is the grams of solute. So the rest of this problem, we're basically going to try and find the moles of solute and then push it back into the molar mass equation to find the molar mass of azolene. The delta T equals K times M. All right, delta T for this problem is the difference between the solution and the pure solvent boiling points, 0.130 degrees Celsius. And delta T equals K times M. We've got the K for benzene, 2.53. So let's solve for molality. Molality, 0.130 is the delta T divided by 2.53. That comes out to be 5.14 times 10 to the minus 2 molal. And that represents moles of solute per kilogram of solvent. Well, 99.0 grams is the grams of solvent. We can turn that into kilograms and multiply it by the molality to get moles. So the 5.14 times 10 to the minus 2 times the kilograms of solvent, 0.09990 kilograms, that gives you the moles of solute, moles of azolene, and that's 5.05 times 10 to the minus 3 moles. All right, that's what we were looking for. Now we can solve for the molar mass because 0.640 grams of azolene created this effect, which was 5.05 times 10 to the minus 3 moles, grams per moles, molar mass 127 grams per mole. That's the molar mass of azolene. This is a really cool technique. If you want to do this kind of quick and dirty, the little equation there in purple, molar mass equals grams of solute times the K value divided by the delta T and the kilograms of solvent. This is something that I've used quite a bit, so this equation comes in super handy. You don't have to. You can also go through the steps in this problem. This process works for both boiling points and freezing points. So in this problem, it was how much higher the solution was relative to the solvent in a boiling point. You could also do this for freezing point. The delta T would be the difference between the freezing point of the pure solvent and the freezing point of the solution.
The membrane of an egg is semi-permeable and holds a high concentration of dissolved protein. When the egg is in pure water, osmotic pressure causes water to flow into the egg and it swells. In highly concentrated sugar solution, the solute concentration is higher in the sugar water than in the egg. Now osmotic pressure causes water to flow out of the egg.
The fourth colligative property that we haven't talked about is osmosis. And osmosis is the function of a solution. It creates an osmotic pressure, all right? And the pressure is very, very interesting. So going back to the original idea at the beginning of this lecture, you can take an egg, place it in acetic acid, which is vinegar, and the hard shell goes away. It dissolves. Then you've got just the egg yolk, all right? And if you have the egg yolk in pure water, the yolk gets really big. So you can see in the picture there in the middle, the yolk is much bigger than the egg that it came from, if you will, or the average egg. The water makes the egg expand. On the other hand, if you put that egg in corn syrup, you can see that the yolk shrinks down quite a bit. So we're seeing here the effect, and osmosis is the effect of the solvent in the solution. It's actually creating a force. It makes the egg get bigger when it's pure water, and it makes the egg get a lot smaller when it's in corn syrup. So let's talk about what the heck osmosis or osmotic pressure is all about. In osmosis, you think about osmosis as there's like a solution on one side and pure solvent on the other side. And there is a semi-permeable membrane that separates the two. And the semi-permeable membrane usually allows solvent to go back and forth, but the solute on the solution side has to stay there. All right? So the semi-permeable membrane just allows solvent to go back and forth, but the solute is stuck on the left-hand side of that picture. Solvent molecules move from the pure solvent to the solution. It's almost like they're attempting to make both the solvent and the solution have the same concentration of solute. So what happens is your solution will start at a molarity. Let's say it's 1 molar, all right? And you put it in an osmosis thing like this one. The solvent rushes to the side of the solution, and your 1 molar value goes down. down. Maybe it goes down to 0.1 or even less. This is actually an effect of something called entropy. Entropy is a really cool subject. I love talking about entropy, but we have to wait on talking about entropy until Chemistry 223. It's very, very cool. But for right now, just realize that there's a reason why solvent goes to the solution. It's trying to make the concentration of the solute in the solution go down, be more like the solvent, if you will. It has to do with entropy, but I have to leave that right there. I can't talk about it, even though I'm like, it's really driving me crazy to not talk about it, but you can look it up online if you can't wait to Chem 223.
When a solution of higher concentration and a solution of lower concentration are separated by a semipermeable membrane, one through which solvent molecules can pass but through which solute particles cannot, solvent molecules will pass through the membrane from the side containing the more dilute solution to the side containing the more concentrated solution. This process is called osmosis. Solvent molecules actually move through the membrane in both directions, but because the concentration of the solvent is higher on the right, solvent molecules on the right collide with the membrane more frequently than on the left, resulting in a net flow of solvent from right to left.
As the solvent, which can get through the membrane, passes to the side of the solution, and by the way, the solute molecules are usually bigger because they're hydrated or something like that, so they can't get through the membrane. But anyway, the solvent rushing to the other side actually creates a pressure, and it can push the column up. In the little YouTube right there, you can see that the orange side is like pushed up a little bit, and the blue side goes down. In the picture on the left-hand side, you've got a semi-permeable membrane, and the water is essentially rushing into the membrane, and it pushes the water column, or the solvent column, I guess I should say, up. And the height of the column can literally be measured in millimeters of mercury, just like we saw the regular pressure does. So these pressures are real. They can be measured with manometers and stuff like that, or you can actually measure it with a ruler, as in these cases, to figure out how much force osmosis is producing. And again, it's the effect of the solvent going to solution, all right? Solvent is rushing to the side of the solution, trying to make the concentration go down. Osmotic pressure gets the symbol capital pi right there. Now, pi is the same symbol that's used in math, the 3.14 number, but this is a totally different pi. This is the pressure of the solvent in a solution. So I think the reason why they use pi is that P is usually the symbol for gas pressure. Pi is like the equivalent Greek of P, but of course this is a solvent pressure. Anyway, osmotic pressure pi, which is the same as osmosis, osmotic pressure pi equals ICRT. Now, C is the concentration of the solution in moles per liter. I, if you need it, is the Van Hoft factor we talked about in the last section. So ionic compounds will have I's of 2, 3, stuff like that, but the organic covalent pieces will just have I's of 1. Now, R here is the good old gas constant R, 0.082057. It's the same R we used in PV equals nRT. That R is also used in osmotic pressure. And finally, T is the Kelvin temperature that you're going around. So you can actually calculate the osmotic pressure. It's going to be in atmospheres if you use this equation. And that osmotic pressure has a lot of interesting things you can do with it.
When a solution and a pure solvent are separated by a semi-permeable membrane, solvent can flow in both directions, but the solute cannot. Here, pure water moves into the solution, working to bring both the solution and pure water to the same concentration. This process, osmosis, continues until the flow of water across the membrane is balanced by the pressure exerted by the water column. A semi-permeable membrane blocks solute molecules, but allows solvent molecules to pass in both directions. The number of solvent molecules moving from the solution side to the pure solvent side is less than the number moving into the solution side, resulting in a net flow into the solution.
So both of these videos show again the effect of osmosis and how it creates an actual pressure, all right? The upper left one, when it pushed the column up, you can actually measure that pressure. It's usually measured in millimeters, centimeters, stuff like that. That can be translated to atmospheres. And then the one on the right I kind of like. It shows that semi-permeable membrane. There's like little tiny holes in the membrane. Solvent molecules go through, but the solutes don't, all right? And the solutes don't because they're either larger molar mass, or if they're ionic, then they're hydrated with water molecules, the ion dipole force. So the water molecules go back and forth, the ions stay on one side. And again, the tendency is for the pure solvent to rush to the side of the solutes. It creates kind of a smaller concentration. Concentrations go down. That's the effect of osmosis. And again, it can be measured as millimeters of mercury or atmospheres, all that kind of stuff. Here's a question which uses osmosis to calculate a molar mass. So just like we saw freezing point and boiling point, you can calculate a molar mass. You can calculate the molar mass through osmosis as well. It's usually used if you have a really big biomolecule. And in this example, we're going to calculate the molar mass of hemoglobin. Hemoglobin is one of these big organic molecules, which is just crazy. But anyway, I digress. Let's say we take 35 grams of hemoglobin and we make a liter of solution, and they measure the osmotic pressure pi to be 10 millimeters of mercury. So they put literally a ruler and it comes out to be 10 millimeters, and that's at 25 degrees Celsius. We can use this information to calculate the molar mass of the hemoglobin. Now pi, the osmotic pressure, equals ICRT. I isn't going to be very useful to us here because hemoglobin is big and organic. You don't need I factors when it comes to organic things. You only need I factors with ionic compounds like sodium chloride. So I here will be just 1. We're first going to solve for the concentration, the moles per liter, and from that, because we have 1 liter, we can turn it into moles, and then grams per mole will give us the molar mass. So the first step here, we've got to get the osmotic pressure in atmospheres. 760 millimeters of mercury per atmosphere means 10 millimeters of mercury is 0.0132 atmospheres. That's the osmotic pressure pi. That's going to equal CRT. We can convert 25 Celsius into Kelvin to do temperature, R is 0.082057. So the only thing we don't know then is C, the moles per liter of this solution. So if you do that, you get 5.40 times 10 to the minus 4 moles per liter. That's the molarity of this hemoglobin solution. Now we have exactly 1 liter of solution, so that means that we have exactly 5.4 times 10 to the minus 4 moles. So if you take that 35 grams, divide it by the moles, you get the astonishingly big 64,800 grams per mole as the molar mass. Osmosis is used a lot in biochemistry as a technique to solve for the molar mass of these big biomolecules. It's really cool. Osmotic pressure works a little bit better than freezing point or boiling point changes. Osmotic pressure can be measured and calculated back. It's pretty cool. In the medical field, osmosis is critical. If you've ever had an operation done, they always hook you up to some kind of a bag to keep you hydrated. Well, if they hooked you up to pure water, there would be a problem because pure water would go next to your cells, and the cell, if inside the cell, it's like a molarity, a concentration. And through osmosis, pure water would rush into your cells, making your cells get bigger and bigger, like the egg we saw earlier, right? And after, if you added enough water, the cells would explode, and that would be bad for your body. So the liquids they use are not just pure water. They're usually sodium chloride, potassium chloride, something like that. They have to be isotonic. They have to be the same concentration, roughly, as the cells in your body. So osmotic pressure is absolutely critical when it comes to the medical field. You must use isotonic solutions or else your cells are going to freak out. Freak out in the real medical world, not a very science term, my apology, means that the cells will either go to hypotonic or hypotonic, all right? In a hypertonic, then what you means is the liquid molecules, the little blue molecules inside that cell are going to all rush out, all right? And if they all rush out, the cell will shrink down. On the other hand, if you have pure water, then the water molecules on the far right are going to rush into the cell, make it bigger, bigger, bigger. That's going to be hypotonic. You want to have isotonic, where you have water molecules going into the cell and water molecules going out of the cell. And you can do that if the outside solution is about the same concentration as your cells. And there are ways to figure that out, stuff like that. Reverse osmosis is really helpful, and it's becoming more and more important for better or worse. It's used to desalinate water, so you can take seawater, which people can't drink, pull the salt water, the salt part of the salt water out, and pure water comes in. Now, this is a really interesting kind of process, and it involves super high pressures. So if you add something like 30 atmospheres or more of pressure, all right, to a saltwater system like seawater, the high pressures actually push the solvent molecules out of the solution. That's really against what normally happens, but it does work. High pressure systems, you can get pure water out, and this will create pure drinkable water. And that's really important for places with water shortages. So in the Middle East, that was the first places I had ever heard that they were using this, but now they're using it in Florida and Los Angeles and lots of big metropolitan areas where water is a little bit of a privilege sometimes. This creates more drinkable water. It is a pretty high energy process because you need to have very high pressures to force the water molecules through. In the lower right-hand corner, there's a picture from a water salination plant. Each one of those tubes has a semi-permeable membrane in it. They have super high pressures. They push the water through. Then you have water for drinking, etc., etc. Now, in addition to solution, there's also other kinds of homogeneous solutions. And solutions, like I talked about, are the most important for chemists, but there are other ones. Now, a regular solution is different from the other kind because the particles, the solute particles especially, usually between 0.2 and 2 nanometers in diameter. So salt water, most acids and bases, stuff like that, fall in this category. The other types of solutions, one of them was called a colloid. And a colloid is also a type of a solution. It's a homogeneous mixture, but the particles are quite a bit bigger. They can go from roughly 2 to 1,000 nanometers, and these are a lot bigger. So this is going to create things like milk is actually a colloid because it is one homogeneous solution, but it's different. Fog is actually a colloid, which is kind of cool. And in addition to solutions and colloids, you also have suspensions. Suspensions have the largest particles, and these are things like blood, paint, aerosol sprays, lots of examples. Now again, most of the time chemists are very happy with just solutions, but colloids and suspensions absolutely have cool uses too. And I want to talk about them real fast. And again, the difference between these, they're all homogeneous mixtures, like it's just one phase. But because colloids and suspensions have larger particles, you're going to see some different effects with those that you don't see with solutions. There's something called the Tyndall Effect, and the Tyndall Effect is a way to detect if you have a suspension or a colloid versus a regular solution, all right? If you place a laser or some light beam through a colloid or a suspension, you will actually see the laser beams go through, all right? And so in the picture in the upper left kind of there, they're pointing a laser, first of all, through pure water, and you don't see the laser beam as it goes through pure water. But on the other side, then, you have then some colloidal silver. And the silver actually is a colloid, all right? It's got bigger particles in it, and it makes the light, if you will, like diffract a little bit. So you can actually see the light source as it goes through a colloid or even a suspension for that matter. If you use just regular solutions, you wouldn't see anything either. But man, when it comes to colloids and suspensions, you absolutely do see it. And this is what the Tyndall effect is all about. Tyndall effect happens because those bigger particles are able to interact with light. They make the light beams refract and move around a little bit more so you can actually see them. If you've ever been hiking and you sometimes see the light coming through the fog, sometimes people call those Jacob's ladders. Those Jacob's ladders are the Tyndall effect of the light going through essentially a fog. And a lot of times the light in sunsets and sunrises is also the effect of the Tyndall effect. Colloids and suspensions have a type of solute and solvent as well, but they usually call them different things. The solute is the dispersed phase, and the solvent is the dispersing medium. And all the things on the right are examples of these different types of colloids and suspensions. So you're seeing things in there like milk and yogurt, bronze, shaving cream, smoke. All of these things are also types of homogeneous mixtures, but because the particles are bigger, you're going to see these different effects. You'll see the Tyndall effect and stuff like that. So it's really interesting. There's a lot of colloids and suspensions around us all the time that make things much more interesting.
In untreated cotton, surface hydroxyl groups attract each other and make for a rough surface. Fabric softener molecules are surfactants. Their polar heads are attracted to the hydroxyl atoms, leaving their nonpolar hydrocarbon tails out. The tails, because they display weak intermolecular force, can slide past each other, thereby imparting a soft texture to the cotton. In untreated cotton, surface hydroxyl groups attract water molecules, so cotton absorbs moisture. In cotton treated with softeners, however, some hydroxyl sites are occupied, making the fabric less attractive to water and therefore less absorbent.
Surfactants, which are also known as surfactant emulsifying agents, promote the formation of colloids by coating dispersed phases, preventing the formation of large particles. So basically, these are like soaps, all right? And the soaps, if you will, basically have a little positive or sometimes negative end, and they have a big nonpolar body, all right? So in the last part of this video right here, you see some little positives in a circle with a kind of a squiggly line to the right or left of them. Okay, so the positive charges then are the positive part of these detergents. Detergents are just ways to clean things. And then the squiggly line off to the side, that's basically a non-polar chain, usually of carbon atoms. And you're probably thinking like, what the heck, all right? Well, if you get a stain on your shirt and you want to clean it off, all right, water is really good about taking out ionic compounds. So if you get sodium chloride on, all right, no problem. The water will clean that right off. And water's pretty good about taking out things like sugars and stuff like that. But what if you got a non-polar substance on your shirt, like a stain or something like that? Well, the polar things aren't going to do as well. You need more than water. And so these detergents and surfactants, they have both an ionic side and a non-polar side. And that squiggly line represents the non-polar part. And the non-polar parts can attract themselves to the stain, if you will. They'll surround the stain and they'll pull it out. It's a pretty cool thing. And I'll show you a video here in a little bit more about how that works.
A soap micelle consists of a group of surfactant molecules with hydrophobic tails pointing inward and hydrophilic polar heads pointing outward. The micelle absorbs nonpolar oily liquids and carries them away as an oil and water colloidal dispersion.
Soaps and detergents, of course, are really useful in our day-to-day world. And the picture down there, the animation showed like if you got a little drop of oil, say, on your shirt, all right? And water wouldn't do anything against oil because oils are usually nonpolar. And of course, water is very polar hydrogen bond. So, but if you put in a detergent, the water is okay with detergents because they'll have a positive or a negative end. So that picture there of that molecule, they've got CH3, CH2, 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 et cetera, et cetera. That's the non-polar side. Water doesn't like that side, but it does like the other side. You have essentially like a type of a sulfate end that's connected with a sodium. That sulfate side will be okay with water. The ions get along well with polar water. But when this soap part here sees the oil, it's not the ionic side, the negative sulfate side that attracts the oil. It's the other side. It's the CH3, CH2, 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 etc., side. That will actually surround the oil. So you have nonpolar and nonpolar, and the nonpolar part essentially gives up its hold on your shirt, and the nonpolar parts surround the oil, but the other side of the nonpolar is still ionic. So the water will rush this big micelle through, which is basically the soap and the junk together, and flush it down the drain or whatever. Woohoo! Cleans your shirt. Life is good and chemistry is awesome.
Why don't oil and water mix? The hydrogen bonds between water molecules are too strong to be broken in order to produce a relatively weak interaction between water and the molecules in the oil. Thus, water excludes oil from entering the aqueous phase.
So when all is said and done, soap and water, all right, have like parts, so they get along okay. But oil and water don't really get along. Oil has essentially nonpolar bonds, and water has very polar hydrogen bonded, if you will, interaction. And people feel that water essentially excludes oil. Water has such stronger intermolecular forces it kind of doesn't want to get along with oil. So soap is just an intermediate then that allows oils to be removed in water in your washing machine or something like that, where they basically make a bridge between the two polarities. And that's really clever how it works out. Of course, soaps are a huge industry and a big part of science and chemistry and engineering and all that kind of stuff. This will at least give you an introduction to some of the details that go in. Pretty cool stuff. Okay, that's the end of chapter 11, and I really appreciate you spending your time with me. This area has a little bit more math than some of the other areas, but it's all stuff you can do. I do recommend that you go through the examples, make sure that you know how to do it. To further your studies, I do recommend looking at the study guide, which is just a bulleted list of the highlights from this section. The concept guide will have actually worked examples, and I definitely encourage you to check that out. And of course, after this slide in the lecture notes, there's an important equation slide, and there's also some end of chapter problems where there's a problem and the answers on the next page. In addition to all of that, there is a handout in the companion and on the website called Concentration Units Handout. And if you can't find it, you email me and I will send you a direct link, and that's not a problem at all. But this Concentration Units Handout will go through examples of how to go from molality to weight percent and mole fraction, and also how to go from those three to molarity. And in this area, I definitely recommend you look at those examples, because looking at them will make it a lot easier to figure out. So if you get stuck on this, don't be afraid to reach out to me. Email is a great way. I love to respond. Also, you can talk to the Learning Success /Avid Center, and they will have people there to help you with this stuff as well. Anyway, I wish you the best in your studying, and I hope you have a wonderful day. Cool.